So first of all, I want to say thank you to each one of you for being here this late on the last day. And I also consider that it is fair to say thank you to the organizers for such a nice school. I mean, it's a big effort to bring people all around the world to share ideas. So I want to say thank you, Jose Luis, Jose Carlos, Jose Maria, and everyone involved in the organization of this school. So let's say thank you to them. Okay, so I'm going to talk to you about two problems in applied knot theory in which I got involved in. So the first problem is the confinement of DNA, yeah. And I also want to show you that many advances in knot theory are just like playing a game. So I'm sure you know these two images, right? So this is the snake game in dimension 2. And we also have the snake game in dimension 3. So please keep in mind this image, right? We are going to come back in a few minutes. So what's the confinement in biology or chemistry? There are some situations in which we have molecules in confinement. Yeah, and this confinement could be important for I don't know, biological processes in of the molecule or any other issue. And for instance, here we can see this chromatin structure, which is a high level structure of DNA. So this is not a chain of DNA. If you start zooming in here, one of these is kind of a strand. You start zooming and zooming and zooming, and eventually you're going to see the DNA molecule. So this is the way this chromatin structure is the way the DNA get the structure in eukaryotes, right? Mainly. And this is a famous paper in 2009. I mean, probably you recognize this image. And the problem here was to determine which one of these two configurations here is more suitable to model this problem of the packing of chromatin. Yep. And well, the conclusion here was that the second model, this fractal globule, was the more accurate. Well, I don't have to say what's the importance of DNA. I mean, we know that it probably is the most important biomolecule for life, as we know life. Yeah. And this is the image we have in mind when we listen the word DNA, right? So this was the first time we got an image of knot DNA. Yeah, it was almost 40 years ago, and we can see here that it has structure, so we can see the structure, and this is a kind of a curve, right? Closed curve. So this is a knot. So we are going to represent these circular molecules of DNA by knots. Why is important the confinement of DNA? Well, I just mentioned some situations. For instance, when the DNA molecules should go through some surface, which could be, I don't know, cellular membrane or some synthetic surface. So it's important to know how wide this molecule is, right? And also, this is another example. This is the image we have of a virus, right? So this is the capsid of the virus, and the DNA of the virus is contained here. So it's related to the packing process of DNA in this capsid of the virus. Yep. So we are going to use knots. Let's say a few words about mathematical knots. And a knot is a small embedding of S1 in R3 or S3. So it could be as simple as this one. This is called the trivial knot, or it could be very complicated, right? So the main question here is to say when one of these objects are equivalent. In fact, maybe you can see that, but this is actually equivalent to this one. But let's see what I mean by equivalent. Two knots K1 and K2 are equivalent if there exists an ambient isotopy taking one onto the other. So if we start with this knot, Yeah. If you see here, we are performing local isotopy to get this knot, and we go on. So we perform a sequence of local isotopies, and at the end we obtain this trivial knot, right? So that's the idea of when two knots are equivalent. As you can see, these two knots look very, very different. Yeah. This is a representation of a knot. This is a planar representation of a knot, which is called a regular diagram. So as you can see, there are special points like this one. Yeah. And this point is indicated that we have two arcs and one is above the other. Another important theorem in knot theory says that the two knots with diagrams, regular diagrams, are equivalent if there exists a finite sequence of local moves called Reidemeister moves. And these moves may be of three different types: R1, R2, and R3. So in the previous example, you can see that we are performing a sequence of this Reidemeister move. So from here to here, this is a second Reidemeister move. This is a third Reidemeister move, and so on. Okay, a question for the audience. We know what does it mean for two knots to be equivalent? Which of these four knots are equivalent? Any idea? C and D. Oh. So the experts. C and D. Okay, no. A and C, no. No, the answer here is A, B, and D are equivalent, and C is different, right? So, I mean, it's not obvious. You should perform a sequence of Reidemeister moves. Sorry? And as you can see, these knots are quite simple, and it's hard to decide at sight which knots are equivalent. So fortunately, we have a lot of theoretical tools called knot invariants, and we also have a increasing computing power to compute these invariants, and then we can create these tables of knots, right? So as you can see, these are a list of all knots, and we are listing by the crossing numbers. So for instance, with zero crossings, we have only one knot. With 3 crossings, we have only one knot. 4, we have only one knot, and so on, right? So we have a lot of information concerning knots. I'm going to present to you 3 models for knots, because we want to implement some algorithms in the computer to decide, to study the problem of confinement of DNA, right? So this is the first representation. It's called the closed braid representation. Yeah. What is a closed braid? If you look at this point, the red point, so the knot is winding around in one direction, right? So it's only clockwise or counterclockwise. And if we cut this knot along these three strands, what you get is something like this, right? So this is called a braid, yeah? And the braids are important because they have an algebraic structure. So what's this algebraic structure? Imagine you have a braid with 4 strands and another braid with 4 strands. How you operate them? Just concatenate, right? That's the operation. Which are the generators? Well, take 2 consecutive strands like this and just twist them. Yep. So, for instance, here you can see that we can see the sequence of generators along the braid, right? And we also have relations. The first relation is that 2 of the generators commute if they are not consecutive. Yeah. And the second relation is a kind of a reformulation of the Reidemeister move number 3. Okay. That's the first representation. There is another representation which is very interesting by Colin Adams. This is called the petal diagram representation. So the idea is, suppose you have your regular diagram. Yeah, this diagram may contain many crossing points. So you are going to shrink all these crossing points into a single point. Yeah, and what you get is something, well, probably not like this, but you get some arcs that could be nested. Yeah, so but there is an algorithm to put in such a nice position as a flower. Yeah, so the information of the node obviously is not in the crossing, on the multi-crossing point, because you have all crossing concentrated here, but the information is in these numbers, right? So you can see this kind of a flower, but what if I see the flower in this way? So this point is going to be an axis, right? So you pick a set of points at different heights or levels in this axis, and that's what it is indicated, this number. So the first arc or the first petal goes from the first level to the third level. This one goes from the fifth level to the second level, and so on. Yeah. So this representation is also important because it has, as you can see, it has a combinatorics behind, right? There are some permutations here, so it's interesting to do some statistical analysis in this model. Finally, the polygonal nodes. So I mean, I think it's clear what the polygonal node is. It's just, instead of having a smooth node, you can put your node in a position in which you have a finite number of line segments, right? So we have three models. Which one do you consider that is better to represent the circular DNA molecule? So we have a braid representation. We also have this petal diagram, and we have a polygonal node. Which one? Yeah, so for instance, no, only two strands. Yeah, but yeah, look. So you have this model of DNA, right? Something like this. But in the model, we are representing this two strands model as a single arc. Yeah. Yeah, the last one. But look, not any polygonal node, right? Because if you look at this point, you can have small angles. Yeah. But in the molecule, you have some constraints that don't allow to have small angles. And you also can have two arcs which are very close, but again, the molecule is a physical object, and it is not possible to be that close, right? Okay, that's a model, but not that model. It's a variation which is called the self-avoiding polygon model. Yeah. So what is a self-avoiding polygon or a cubic knot? Take a polygonal knot, but in the skeleton of the cubic lattice of R3, right? So what's this? If you remember the game of the snake, this is something like playing the game of the snake in dimension 3, right? Well, we have some question when we see something like this. For instance, what is the minimal length of a self-avoiding polygon of a knot type K? Yeah. To know this number could be related to the minimum number of nucleotides to form a DNA molecule. Yeah. And there is also a problem concerning the confinement of this self-avoiding polygon to different models. So we have the two-slab model, which is take two parallel planes, and the knot is here, right? Or the tube, you have to consider 4 planes. Yeah. And finally, a box it's a box, yeah, and try to realize a knot in this confinement. Yeah, these are difficult problems. These are very difficult problems. So we can define the minimum step number of a knot as the minimum length of a self-avoiding polygon of a given knot type K. So here we have two representations for the knot for one. This one, I think it should have 30. The length of this curve should be 30. And in the case of the knot phi 1, it should be 34, I think. Yep. So it's difficult, I mean. And we also can define the minimum Prince volume of a knot type, which is the minimum volume box containing a knot type, right? So look at these two representations of knot 3.1, yeah? But this is in a box of volume 3 to 18, and this is 16. So the volume here is less, right? Okay. The problem is try to fill in this table. So we are relating the minimum step number in different confinements. So this is the minimum step number in R3. For the threshold, it should be 24. But as we see, when we put some constraints on the confinement, the number of steps increase, right? And well, this table is incomplete in some cases. I'm not sure about if there is a complete table, at least for these knots, which are torus knots. But how can we work on this type of problems? Well, we have an analytical approach. I show you this theorem by Ishihara, and says that a knot or link of type K can be confined to this tube m times n, if and only if the trunk, I'm not going to say what the trunk is, if the trunk is bounded by this number. Okay, the important here is the argument, the main argument they give, and this is the idea. So you have a braid here, see, a braid with 8 strands, yeah. So you are performing some braid operations here at each level, but they represent these operations via these diagrams. Do these diagrams remind you something? It's okay? Sure. I don't know the name in English. It should be number puzzle or puzzle number or something like that. Well, no, it's not a magic square. There is a free square, and you can move this square to this empty space and form some configuration. Yeah. So again, as you can see, sometimes the arguments are just playing a game, right? Okay, we also have a computational approach. This famous algorithm, VFACF. And this algorithm has two moves. This is the first move, and this is the second move. And it says that two self-avoiding polygons of the same knot type differ by a finite sequence of this type of moves, right? So as you can see, it's the moves are quite simple, but it's again, it's difficult to find a sequence of steps to go from this configuration of the triple knot to this other configuration. It's difficult, but we can use the algorithm to perform simulations, study the behavior of this type of curves. Yep. So these are the conclusions. For this representation of knots, we want to determine the minimum step number of a knot type K. We also want to determine the minimum Prince volume of a knot type K, and also if there exists a relation between these two invariants. If in particular, I'm interested in determining this number for torus knots. Yeah, for torus knots, right? So that's the first application. Any comments or questions? I'm going to move. Yeah.
So I currently not in water size. And since you previously mentioned that you care about the minimum size of the body, in which you can like embed the knot.
Yeah.
Do you also care because I imagine if you try to go from one to the other with these kind of moves, you will need more space throughout connectivity.
Yeah. Sure. The space could increase, but also could decrease, right? So you can apply each sequence of these two mobs. As you can see, this doesn't change the minimum step number, but this increase in two, in two, or decrease in two, right? Yeah, but you can use any sequence, so the numbers change. That's the difficulty of this problem. Yeah.
Well, since the DNA doesn't make polygons, what should the vertices be, like physically, or what do they represent? Or is it just a way to turn it into?
You mean the vertices? Well, I mean, as I mentioned at the beginning, we want to use a computer, right? So in this case of knots, it's important to have vertices, right, instead of having a smooth knot. But they have no meaning, right? Okay. Any other question so far? Yep. Bridge.
Number of
Bridges.
when you move around in the plane and you just put bridges.
Yeah, that's the next problem. But yep. Which one? Here.
In the plane, wander, you can put complete draw without in the upper plane, you can draw the first.
Well, there is, there is something called bridges in knot theory. I'm going to that point, but I'm not sure if that's what you are trying to say. Okay, so maybe if I explain a little bit more about bridges. Any other question related to this problem? No? Okay. This is the second model. Is the Geoboard model. This was introduced by myself a couple of years ago, and I'm sure you recognize this subject, right? I mean, when I was in elementary school, it was an activity to construct one of these. I don't know if it's still the case, but well, it could be dangerous without parental supervision. And we have some variation of this Geoboard model. Yeah, it could be circular. And we put here some rubber band or stamen or something to produce figures, right? So how is this related to knots? I'm going to talk to you about the 1-1 knots, or also called one bridge torus knots. And this is the name bridge, right? What does it mean? The first one, here there are two numbers, right? 1 and 1. The first one means genus 1 surface. So genus 1 surface here is a torus. Yeah, it should be orientable. And one bridge means that you take the product, the topological product of this torus with the interval. Yep. So we can represent it this way. And you have here in this product the knot. Yep. And the second one means that you have only one maximum or only one minimum. Yep. So what you see is 2 points. And inside the product, you see two arcs. winding around like crazy. Yeah. I mean, this is a simplified diagram of what's going on, but it could be something like this, right? This is not even so complicated. So maybe you can see here a torus somewhere, right? But where is the maximum and where is the minimum or whatever? It's difficult. Huh? So here's the bridge. Here, this is the bridge. And the idea, well, before I present the idea, is I want to say to you that there are some called normal forms of 1-1 knots, which are a little bit complicated. Yep. So you start with this model. So you need 4 numbers. Yep, like this 4 tuple of numbers. Then put arcs as indicated by the number. And if you get one component here, then they provide an algorithm to embed in a torus. Yep. So don't try to figure out what these numbers mean here. But this 1-1 knot is represented by this 4 tuple. And this is a sign. And there is another form called the Conway form. In this form, you need 4 tuples, a finite number of 4 tuples of integers, right? And again, it's a difficult representation of knots. So I'm going to present the idea. So what's this Geoboard model? So start with your knot, yeah? So the idea is you have 2 arcs, which are transversal to every level torus, and put one of the arcs in a vertical position. It means that one of these arcs is of this form. So pick a point, zeta 0 here, and this arc is represented by zeta 0 times 0, 1, right? And then we have our knot here, or arc, this arc which is winding around. So you can project the arc onto the torus, yeah? And then you can take the lifting of this arc to the universal cover of the torus. So what's the universal cover of the torus? For topology students. Which one? R2, yeah, it's the plane. It's a plane. So when we take the lifting of this curve, we see something like this. Yeah, we see something like this. And what are these points? Are the preimages of this point under the covering function? Yeah. So you know that there should be an infinite number of these points. So this curve should be disjoint from this point. Yeah. So let's take small disks center at this point and remove them. So that's a multipuncture plane, and in particular is a metric space. You can take the minimum length representative of this curve. Yeah. So what's this? It looks like the Geoboard model, right? So this arc is represented by this arc. And we can say even more. This arc starts with this segment of line, and then we have here an arc around this circle, and then again a segment line, and then again an arc around this circle, and so on. So we can parameterize this curve. So this is the parameterization. We have one of these knots. So we start with the slope. This line segment has a slope. So this is the slope of this curve. Then we have the number of half twist around each circle, and then again a slope, and so on. Okay, so maybe you are not impressed, right? I mean, it's such a nice representation, but we as topologists ask how many of these representations exist for a given knot. So in the case of a subfamily of knots, so we started with 1-1 knots, Now we add this adjective, G satellite. A satellite node is simply, suppose you have a node. So this is called the companion node, and a satellite is a node which is winding around this node somehow. Yeah, it's what a satellite does. But in this case, we have the theorem by Morimoto and Sakuma that every satellite, one node, is satellite, but not of any type of node. It should be a torus node, and it should have a rational link pattern. So what does these words mean? Well, I think torus node, you know what is, right? This is a torus node. And here we have the rational link pattern, yeah? It's called also a two-bridge link. These are the bridges, yeah? And how's the construction? Well, look, this framed node is trivial. So we are in S3. So the exterior is a solid torus, right? So we take an homeomorphism from the exterior of this node into a regular neighborhood of the torus node. Yeah. So where is the node? The node is the image of K2 under this homeomorphism. Yeah. So well, that's a satellite one node. But the important part here is that in this case, the number of parameterization is at most 4. We have 4 parameterizations for this node, and in fact they are related. These 4 parameterizations are related. I'm going to explain how they are related. To construct this Geoboard model, we start with a vertical arc and the other winding around, right? So change the roles of these 2 arcs. So the arc which is winding around now is vertical, and the other is winding around. So that's the first. That's the second parameterization. So we have 2 parameterization, and then just change the order of the pattern, as you can see here. So we have 2 more, and that's all the possibilities. So it's nice. Okay, but we are talking about applications, and I found this Dobbin's path. Yeah, Dobbin's path is a shortest curve connecting 2 points in the Euclidean plane with constraints in curvature. So, for instance, take the plane, take some disks, and remove them. Yeah. So you are wondering for minimal length curves in this space. So what's this? It's exactly what we are doing, right? So in some sense, one nodes are representing a special type of Dobbin's path with a disk remove specific points. Yep. And this has importance in well, there are not so elaborated, but 2 models of wheel robots or cars in the plane with some obstacles. Yep. Okay. But what happened in the general case? Well, we have the following result. Every node in S3 admits a G1 position with respect to a compact connected orientable surface of genus G. So instead of having here the torus, we have a surface of genus G. What's the universal covering of a surface of genus greater than 2? Hyperbolic plane. Okay, have you played the geoplane in hyperbolic space? So the generalization follows, right? So I don't know if you find this interesting, and I still have time, but I don't have no more to show. So thank you. Yeah.
Are you working with the biology?
Oh. Yeah. No, as you can see, the model is abstract. I mean, you can work without put this model into a context, but it is important in biology. That's it. So you still can publish something, right?
Another question for me.
Yeah. Which one? The
This kind of projects of maths, I mean, how can this help to people who actually works with DNA in a laboratory?
Yeah, well, there are so many applications. There are some which have more direct applications. So for instance, there are some enzymes called topoisomerases, I think, and they perform local operations in the knot, well, in the DNA, which is represented by a knot, but which are operations in knot theory, like changing the crossing, right? You can go from this to this one. Yeah. Why? Because in the case of DNA, to perform any process like transcription and replication and all that important functions, the DNA should not be very knotted. Otherwise, it's difficult to perform. So it has importance. I mean, it has importance. The confinement problem, maybe it's a little bit far from have direct implications, but well, it's an interesting problem.
Because those enzymes, they work by themselves, but I can understand that it is helpful just to understand how do they work. And also, at the beginning, you talked about this chromatin problem that was solved before.
Yeah. Well, yeah. Okay, look, this is a paper in Science, I think, here, 2009. Yeah, it's Science. And the problem was not, they performed some simulations trying to understand how this chromatin is packed, for instance, in a tree ball, right? So what's the color? You have a strand or stamen, and the color is in a rainbow fashion. Yeah, and you pack this molecule, and what we can see here is that it tends to be packed locally, right, as the colors show. But of course, that's a biological reason. They discard this model, which is a kind of a random model, right? So the chromatin pack locally. Sure. There.
Any questions?
Yeah.
It's about the levels. I reading the register, but my question is mainly because when you look into the applications in DNA and biology, things start getting really knotted. And every invariant that has seen that can actually be like put into a computer program starts running into a lot of issues as the crossing number starts increasing. So my question is, how much of this can actually be programmed, and then how would it behave on structures that are just like that image you have there of the another ball, like that's your how computing.
Yeah. Well, this is a very useful tool, as I say. So the algorithm is a little bit on the contrary. So you start with a knot, and then you start performing these operations to stay in this class, right? It is not you construct any knot and try to make operations there, right? or is
What I mean is, yeah, I suppose in applications that are not would be already pre-input, right? Like maybe some biology can give you, hey, the molecule I found and like this. What the my question is, increasing the number of, like, say, crossing points, I mean, a prediction. How does the complexity of that increase and how long does it take for, like, say, around these algorithms? Yeah.
sure? Yeah, well, in fact, that's a difficult question theoretically. I mean, if you start with a knot and like the first diagram I show, which has a lot of crossings. Yeah, this one. So try to determine what's the real crossing numbers of this diagram is a difficult problem. So, but this is a theoretical difficulty, right? Yeah, I don't know if crossing numbers is a way to try to tackle this problem. Yeah, sure. Yeah, so you start with this diagram, and then you perform. Yeah, I mean, it's difficult to implement an algorithm that recognizes not. Yeah. Well, you can use invariants, but if you have a lot of crossings, compute invariants also could be challenging. Yeah.
Is there any interpretation that, because we talk about knots are being anywhere in this or like
Links? Yeah, links. Well, I mentioned link, but it's a pattern. It's a theoretical model for satellite nodes. But I'm not sure if there are links, for instance, in circular DNA of. Yeah, there should be links. But as I say, these links are not quite complex because DNA tends to be unknotted. Yeah.
All right, let's thank God we did this.
Okay. Thank you.